This video will cover some of the high-level concepts in first-order logic. We'll go over the basic syntax and semantics of first-order logic and briefly touch upon how inference is done or can be done in first-order logic. So, as a review, in a previous video we looked at propositional logic, which is very similar to the Boolean logic we typically reason about when we write computer programs. And we talked about inference in propositional logic, where we're trying to discover whether a certain claim is true. And we can do that by using a truth table where we enumerate every single possible truth value, or by using inference rules that slowly grow the facts that we know about. Right? We start with a knowledge base and we slowly add things to the knowledge base, one step at a time using simple inference rules. And we talked about this sort of magical inference rule called resolution that covers every single possible inference you could make that is a sound inference from a knowledge base. We also talked about horn clauses and forward and backward chaining, which will show up again in first order logic, or at least in this video we're going to think about forward chaining, but there's also an analogous backward chaining procedure for first order logic, and it will again rely on horn clauses to simplify the type of logical knowledge we can encode, which therefore simplifies the algorithms that we have to think about to deal with this type of knowledge. So in first order logic, the plan for the video is we're going to go over the terminology, then we'll talk about these things called quantifiers, which are the most powerful difference between first order logic and propositional logic. Then we'll talk about inference algorithms. So to start off with, we're going to think about terminology. So these are the new terms that will come up in our discussion of first order logic. So almost everything in first order logic is built around these things called predicates. And a predicate is just a function that maps variables to truth values. So you can think of it from a programming perspective. You can think of it as just a function, right? It's a function with a particular prototype, which is that it takes as input a bunch of objects and outputs a truth value, a Boolean value. So an example of this would be, or an example of how these are used, is in these pieces of knowledge encoded here, where we write something like is woman Marge, where we're writing it as if is woman is a function and Marge is its input, and the idea is it will return a truth value. And the other example is mother of Lisa Marge, which has two parameters, right? It takes Lisa and Marge as input, and it's going to output a truth value. And it happens to be that in these examples, based on the Simpsons family, the truth values are true. But drilling further down into the terminology here, what we call a predicate is just the function itself. So is woman is a predicate, right? And so is mother of. Those are predicates. And Marge is a term or a constant, as well as Lisa. And is woman Marge, when we actually instantiate the function call with particular inputs, that's called a formula. And formulas are things that can have actual truth values. So while a predicate is a function that can return a truth value, it doesn't have a truth value by itself. It only has a truth value when you give it actual input. Additionally, more terminology, just like functions, predicates can have different arity, which just means whether they're binary functions, they're three-array, I guess trinary functions, four-array or n-array functions. And this just characterizes predicates by how many inputs they take, right? How many terms they consider when they have to decide whether they're true or false. And then an additional piece to first order logic is that first order logic includes functions which map from terms to other terms. So for example, we might have a function mother of that maps from a person term to another person term. So mother of Bart will return Marge. And this is a very powerful thing that's included in the formal definition of first order logic, but a lot of computer systems or AI systems that process first order logic knowledge will often disallow functions just to make the computational algorithms simpler. So a simple approach for inference is to simply propositionalize first order logic. In other words, convert first order logic to propositional logic. So to do that, what we do is we define propositional logic variables for every single atomic formula. So that means we look at the predicates we're going to be reasoning about and all the terms and constants that we know about, and we think about every single possible way we can instantiate formulas from those predicates and terms, and we assign each of those to just some variable. It's just going to be a Boolean variable. As I've exemplified here, they don't even necessarily have to have a great name. They're just sort of anonymously named M1, M2, W1, etc. And we just have a big now propositional logic system that we can just perform inference in, just the way that we did in the previous video. And this is a fairly nice view of at least a simple example of what you can do with first order logic that at least so far when we've, this is a really oversimplified thing that we're doing, at least it gives you an idea of the type of information that we can encode with first order logic syntax that we can't really do as naturally with propositional logic. Right, so now our variables, we can map them back to some semantic meaning. Right now it's describing the relationship between Bart and Homer as opposed to just some Boolean variable which could mean anything. And it's natural to store these in relational tables because of that, because these predicates are very much related to relations, no pun intended. And you can have, binary relations where it's a relationship between, two individuals, or it could be a unary relation where it's just checking some attribute of the different constants, in this case they're people. And that's okay, but we haven't done really anything that different from propositional logic at this point. And what becomes different when we think about the first order logic, because we have these semantic meanings to these predicates, is that we want to be able to think more generally than thinking specifically about the relationship between Bart and Homer or the relationship between Lisa and Snowball. We want to be able to think about the relationship between any individuals. So that leads us to quantifiers. So quantifiers allow us to encode more general knowledge. So we might want to just think about, people in general. We're not specifically talking to particular individuals. We're talking about particular individuals. We're talking about all people. So we might want to say something like, all mothers are women. And if we want to write that down in sort of the syntax that we've had so far, we would have to enumerate every single possible mother and every single possible woman. So instead, we can use this syntax, which is using the for all symbol, this upside down A, which says that for all x and for all y, is mother of xy, or if y is x's mother, then is woman y. Then y is a woman, right? So for all x and y, if y is x's mother, then y is a woman. This is what's called a universal quantifier because it holds universally for all x and y. And it also, even though intuitively we're thinking about cases where, x and y, or y really is x's mother, this also holds for if y is not x's mother, right? So if y is not x's mother, then we actually don't know anything about the gender of y, at least based on just this one sentence. And that is still logically sound and correct according to this sentence. And then additionally, first order logic has something called an existential quantifier, which says that some instantiation of the variable exists that makes this statement true. So for example, here's a statement. It says, for all x, and there exists a y, such that is mother of xy. So in English, that means that every x has a mother, which is, for the most part, true, since, or at least if we're talking about the domain of organisms that reproduce sexually. So this is great because it allows us a richer way of describing or knowledge in a more general way. However, now going back to the strategy we used before of propositionalizing, it becomes expensive. So imagine we have a a small domain of constants, so just the nuclear family of the Simpsons, and we want to think about the is mother of relationship. So if we want to think about that, then we have to think about every single possible combination of two of these constants, which is not bad. It's not terrible. You can use your basic computer science skills to figure out right away the size of this possible instantiation, which is the cross product here. But it's off the page at this point. I mean, it's 25 different possibilities, and you can imagine how quickly this becomes intractable. Not in a formal sense because it's still polynomial, but it becomes expensive to compute, especially if we have higher order predicates like n array predicates, and then it becomes polynomials to the order of n in terms of how many instantiations there are. So explicitly enumerating all of the possible thoughts you could have with these predicates is expensive. So instead we want to do something a little bit smarter where we only look at things that are relevant. So that leads us to forward chaining, which is analogous to the one that we saw for propositional logic, the form of forward chaining for propositional logic. So again, we're going to limit the knowledge base, the type of sentences that can be in the knowledge base, to these sort of if-then-else statements, and then iteratively chain forward from the knowledge base, growing, adding new knowledge until we hope to find the sentence we're trying to prove. So the input to forward chaining is a set of known atoms, that's our knowledge base, and a set of horn clauses that's also in our knowledge base. So the horn clauses are, again, the implications where all antecedents or all the conditions of the implication and the results are positive. So we're not allowed to say things like, if is mother of A, B, and not is mother of B, C. Right? We're not allowed to say things like that. They all have to be positive, non-negated. So an example is this. This is where on the left side, the antecedent is positive, and on the right side is also positive. So from the input, we have a set of known atoms, and we have a set of horn clauses. You can probably imagine how essentially what we want to do is the same thing that we did for propositional logic, where we plug in things that we know are true into the left side of these implications, and then we get out the thing on the right side. So this is going to be called generalized modus ponens. So we're going to generate new knowledge using generalized modus ponens. And just notationally, we're going to omit these universal quantifiers from when we write down these sentences, just because whenever there's a variable, let's just say by default, a variable means it's going to be universal, and if it's going to be existential, we're going to do something else with it. We're going to explicitly write down that it's existential. So generalized modus ponens looks like this. We're going to consider applying inference using a particular horn clause. So this horn clause here, it has n predicates on the left, which are part of the antecedent, and then one predicate that's the output, that's part of that is the consequent. And the variables, the inputs to these formulas on the left that are made up of predicates and terms, we're just going to call them variable 1, 1, variable 2, 1, etc. just for now. And here's an example of one of these. You might have something where it's is mother of AB and is mother of CB implies sibling AC. Right? I think that's logically correct. It's implying that if B is A's mother and if B is C's mother, then A and C are some form of sibling. So one important thing, which is a little bit hard to notate in the very general form, is that we can have repeated variables in this sentence, in this horn clause. So for upstairs, in the example, you can see that B appears in both the first atom and the second atom on the left. So generalized modus ponens, what we try to do in generalized modus ponens is that we take a knowledge base and we try to find a substitution where we can plug in actual constants from our knowledge base into the variables of the horn clause such that the entire left-hand side is all satisfied. And when we find a substitution that satisfies the left side, we can apply that same substitution to the right side. So if any variables appear on the left, that we use those same substitutions for those variables on the right. And then that new formula that results on the right is a new thing that we've learned through, or that we've inferred through generalized modus ponens, and can be added back to the knowledge base as a new thing we've learned. And once you have the concept of how generalized modus ponens works, it becomes fairly natural to imagine how forward chaining works, right? It's the same concept as before. You start with some knowledge base, and you just keep adding to that knowledge base anything that you can infer using your inference rule. In this case, is just this generalized modus ponens rule, and you hope you eventually land on the formula you're trying to prove. So another thing to think about is how we handle quantifiers. In this case, with substitution, we're mostly talking about handling universal quantifiers. So we actually had to come up with something different to handle existential quantifiers. It's a little bit different. So the universal quantifiers are handled essentially just by treating them as if they're variables that we can substitute with anything. The only restriction is that we have to be consistent with the substitutions, when the variables occur in multiple formulas in the Horn clause. So with existential quantifiers, the way we handle them is that we put them into our knowledge base where we've replaced the existential variable with a new constant. The intuition behind that is that if we know that some variable exists that satisfies this formula, then we don't necessarily need to know its identity. In fact, we don't know its identity. We can never really know its identity if we're just looking at that one existential bit of knowledge. So we might as well just add it to the knowledge base with this new hallucinated constant, and then continue doing forward chaining from there. So at a high level, forward chaining looks like this, and the textbook gives a very formal lower level description. So at the high level, the way I think about it is that you start with a knowledge base, and then you just loop through every sentence in the knowledge base. And for every sentence in the knowledge base, you find all the substitutions that satisfy the conditions of that sentence. And then once you've satisfied the conditions of the sentence, you now know the consequent is also true. So the consequent can then be added to the knowledge base, and you can be explicit about whether you check whether the consequent's already in the knowledge base, or you can just say you add it and just do some garbage collection or deduplication later. And then you just constantly check whether you've found the target sentence that you're trying to infer or trying to prove. And if you don't find it at the end of the search, you have failed to prove the statement, or if you find the opposite of it, the negation of it, then you've disproven it. So of course that's very high level. There's details in how this works, and there's also sort of variants or sort of inversions of this idea, like the backward chaining idea, that also applies using similar concepts as substitution and working from the variable, the formula we're trying to prove, and essentially figuring out antecedents that could have led to that formula, which we will go over in class and are things you can read in the textbook. So just to summarize this high-level video, we went over the terminology around first-order logic, right? The new syntax, the new things that we can do with first-order logic that we couldn't do in propositional logic. So these were predicates, and predicates that take terms as inputs and leading to formulas. I mentioned functions, but I also mentioned that a lot of algorithms will essentially disallow functions to make things simpler. And then, more importantly, I talked about quantifiers, and these are the more useful and more powerful additions to logic that first-order logic allows you. So we're allowed to quantify variables as universal, which means that they hold for all possible instantiations of them, or as existential, which just means that there exists some instantiation that satisfies the statement you're making. And I give you a high-level view of how inference works, where we talked about the differences from propositional logic and how we're going to have to handle the quantifiers by finding substitutions. So we can do things very similarly to how we did them in propositional logic, like with forward chaining, but the key is that we have to explicitly reason about how we substitute, constants for the variables in universally quantified formulas. So we'll go over these and we'll talk about other examples and other variations in class. So I look forward to talking to you then.